Hello, Calculus and Vectors class. Welcome to your very first lesson via e-learning for this course. This is all kind of unexpected and we're still trying to figure things out as we go, but hopefully this will help to clarify things a little bit more than you would if you were just writing the notes down. The idea is that I'm going to try and model this as close to one of our lessons as possible. We're going to go through each section of the note. I'm going to give you a quick explanation of how everything works and maybe give you a few pointers and how to show your best mathematical form. And hopefully that should be enough to give you a better sense of how it works. But if you are still feeling like you're stuck on something, get in touch with me. We'll figure it out and find a way to give you some clarification. But without further ado, let's get into our note. Today, we're dealing with intersections of lines in 2 and 3 space. So essentially the big idea behind today's lesson, if we have two equations of lines, whether in 2 or 3 space, we should be able to analyze them, figure out how they interact with each other, and if there's a solution, figure out how to find it. And of course, part of this you already know in 2 dimensions. And with scalar equations, you're already very familiar with elimination and substitution, so that will factor in a bit here, but we're going to learn some other methods to help us out a bit. Before we do that, let's quickly review the 3 different ways that lines can intersect in 2 space. Option 1 is that there's exactly one solution or intersection point if the algebraic solution to a system of linear equations yields a unique pair of numbers. Essentially, it's an intersection at one single point, and you're going to have an x value and a y value, like this here. Now, the second option is that we could have two coincident lines that have infinitely many solutions. And if we try to solve that using elimination and substitution, you'll remember that we get something to the effect of 0x equals 0 or 0y equals 0. Essentially, it's just asking what values of x or y are going to satisfy those equations. And of course, we know any value of x or y is going to multiply with 0 to get 0. So anything is going to work. Now, option 3 is that we have 2 parallel and distinct lines, and that means that we're going to have no solutions. And when we use elimination or substitution, it's going to look something like 0x equals 7 or 0y equals 7, which is essentially saying which x or y values on our line are going to satisfy the intersection of those 2 lines, or are going to multiply with 0 to get 7. And we know that nothing can multiply with 0 to get 7, so we know that's nonsense. So it means that we have a nonsense answer, which means that it doesn't work for us. So those are 3 options. Hopefully that's not a review for anybody, but just to review how those look when we're dealing with solutions. Now, let's deal with a specific one here. This is 2 scalar equations, line 1 and line 2. That's asking us to find the point of intersection. Option 1 is very, very simple. You guys know this elimination. All you're going to do is you're going to multiply them both to eliminate a variable. So we're going to multiply line 1 by 3 and line 2 by 2 to get them both up to 12x. And you notice that when you multiply those 2 out, we get the same equation, which means that if we try to subtract them out, we're going to get something like 0x minus 0y equals 0, or 0x equals 0, or 0y equals 0. We're just kind of taking that, we're reducing it down a little bit. So that means that we're going to have infinitely many solutions or coincident lines. Again, that's just asking, we're just asking ourselves, with 0x equals 0, what x values on our line are going to satisfy that equation 0x equals 0? And really, it's just saying what x values multiply with 0 to give you 0. And the answer is all of them. So all of the x values are going to satisfy our system of equations, and all the y values are going to satisfy them. So they're coincident and infinitely many solutions. Method 2 is a little bit different. Just because we have vector methods now, we're going to look at this one really quickly. Okay, and this one is asking us to examine the normals. Now just think back really quickly. The normal, when you have your equation of a line, we're going to have that normal vector that goes parallel to it. And we know that if the two lines are parallel, then the two normal vectors should be parallel as well. So essentially, that's all we're doing here. We're going to look at those vectors and see if they are running parallel to each other. So think back. We said in a scalar equation for a line in the form ax plus by plus c equals 0, our normal is going to be ab. So what that means is that we're going to take the a and b coefficients from our two equations, and we're going to rewrite them in vector form, just like we did down here. And then all we have to do is compare. And we want to see if they're running parallel, which means, are they scalar multiples of each other? Can we multiply one of those two vectors by a scalar to get the other? And we're just writing that down here. We're essentially writing that in this form here. We're gonna assume that there is some scalar k that we can multiply one of our vectors by. That's going to give us it's going to give us the other one. So in this case, what we're going to do is we're going to try and solve for k. Now, we don't like solving when we have vectors because it gets very, very complicated. So what we're going to do is we're going to separate it out into an x equation and a y equation, just like we did here. So x equation and y equation, just taking the x values out of our two vectors, 4 and 6, and then for the y equation, taking the y values, -6 and -9, and rewriting that as if there's no vectors there, just our x's or y's. Almost like the same idea as if you were rewriting your parametric equations. Same basic principle. And all we're going to do there is we're going to test each of the x's and y's to see if we get the same value of k. We rearrange it and we see that, hey, we have 2/3 as our k value, which means that if we multiply normal 2 by a factor of 2/3, it's going to give us normal 1. So in this case, we know that the normals are scalar multiples and the lines have to be coincident or parallel and distinct. So now we just need to determine which one it is. So we're going to look at the equations now and take a look at the equations. We know that we multiply them out and we get the same a and b values. So everything's in proportion. We just need to show mathematically that our c values are in proportion as well. And we notice that line 1, we can get that by just taking line 2 and multiplying everything by 2/3. So we can say line 1 is equal to 2/3 times line 2. So therefore, the lines are coincident because the c values are in proportion. So again, either method will work for you. If it's not asking for one specific method, you can use either one. But you're going to see how this second method comes in handy when we deal with more complicated problems in 3 dimensions. So keep that kind of handy. Let's go on to question B. Now in this one, now we don't have scalar equations anymore, we have vector equations. So now we have to use some slightly different methods to help us out. So the first thing we're going to do to make our lives easy, always we're going to take them and we're going to rewrite them as parametric equations, just like we did here. Just because we know doing math with vector equations is always a little bit tricky, so having the parametric equations is going to be a lot easier. Now from there, now we're going to start using a bit of substitution and elimination, because you can see we have x's and y's, s's and t's. So we have too many variables. What we're going to do is we're going to get rid of some of them. So our first step is we're going to take our x equations and we're going to set them equal to each other, just like we do down here. And then we're going to take the y equations and set them equal to each other, just like we did here. And what you notice is that once we do that, the x's are totally factored out and the y's are totally factored out, and we're left with just s's and t's. In fact, we have 2 equations with only s's and t's. We know that's just a system of equations, so all we're going to do is solve using substitution and elimination, like we do down here. Hopefully that's not too tricky for you guys. Like I said, it should be child's play for you at this point. The only thing I will mention is I put these ... dots just because I don't think you need to see me do all the steps If you do, just come and ask me. I'll be happy to explain it. But for your solutions, make sure you include those steps. Okay. But as once you go through and do that elimination substitution, we get a result of 0t equals 16. Now, once we get to that result, just like before, we have to ask ourselves, what does that mean? So basically, we started this on the assumption that we would have a t-value that would give us an intersection of our lines. So basically, this is telling us what value of t is going to give us an intersection between our two lines. It's going to lead us to a point. So in this case, we need to find a t-value that multiplies with 0 to get 16. And of course, we know nothing works. So in this case, there's no solution. It has to be parallel and distinct. So that's method 1 to try and solve this one. Method 2, okay, very similar to method 2 from the first option, and the reason why that and the last one we dealt with normals. We said they have to be parallel if the lines are parallel or coincident, but we know that the direction vectors will work as well. So same basic method. We're just going to use the direction vectors this time. Now, when we get to planes, this method isn't going to work so well, but for right now, it'll work just fine for us. Now, just like before, we're going to compare our direction vectors and see what they look like. In this case, we have -6, 8, and 9, -12. Now, we have to ask ourselves, is there a relationship there? We can see that they are scalar multiples because we know that if we multiply if we multiply the first one by -1.5, then we get the second one for both x and y. But we need to actually use good mathematical form. So let's go through and do the solution. So just like before, we are going to rewrite it. Direction vector 1 is equal to k times direction vector 2. And then we're going to separate it out into x and y equations. And then we're going to solve for k. And if we get the same value for k for both, it means that the same number works for x's and y's. So we can use that to help us solve it. And of course, you see that with this one, we get -2/3 for k for both our x's and our y's. So in this case, our lines are either coincident or they're parallel and distinct. So now that we've shown that they're parallel and distinct, now we need to figure out which one it is. So the little trick is we can test one point from one of the lines on the other line and see if it satisfies the equation. So what that's going to look like, we're going to pick a point from our equation. Let's pick 2, 1 because that's on line 2. So this one here, we're going to sub in, and we're going to try and solve it. So we're going to take 2 and plug it into the x equation, and 1 and plug it into the y equation. And when we do that, we see that we get, for the x equation, we get -1/6. And for the y equation, we get -1/2. So something is not adding up there. It doesn't make sense. So essentially what that means is we started this, we were making an assumption that that point on line 2 fits on line 1. We get something that doesn't make sense. It means that our assumption was false. So our assumption that the line fits on line 1 is false. So because the s values do not match, the point is not on line 1. Therefore, line 1 and line 2 are parallel and distinct. Because the point does not fit on line 1, they don't have. If it's an all or nothing proposition, we can have either all the points on our line, or we can have none of them on the line. So because one of them doesn't fit, none of them fits. By the way, one more thing I'm going to mention to you really quickly. This little symbol here, it looks like an upside down therefore. That means because, and usually it's kind of to help clarify the justification with a therefore statement. You'll probably see it when you go to university in solutions, so I'm going to make sure you're aware of it now. So we're going to use that from time to time, so just be aware of that. Now we finished off with with two lines in two dimensions. We dealt with all the different ways to solve with scalar equations and vector equations. Now we're going to go into 3 dimensions. So in 3 dimensions, it's very similar, except it changes a little bit. So our first 3 options here are pretty much the same basic idea. The first option is that we have an intersection at a point. They're not parallel, but they still intersect at a point. Option 2 is that they're coincident lines. Option 3 is that they're parallel and distinct, so no solutions. And the fourth one is a little bit different. In 3 dimensions, because we're not limited to one single plane, because we're not drawing on a flat board, they have to cross each other. But let's say, trying to come up with an example here, but one isn't coming to mind, so I won't worry about it. But you can see in the example there are some possibilities where you can have 2 lines in 3 dimensions where they don't intersect at all, but they're not parallel. So we have a special name for them. They're called skew lines. And there's no solution because they don't intersect. One more really important thing I want to mention to you guys, which becomes really important when we're trying to narrow down our options. The way that we test, that we start to narrow down the options is by looking at the direction vectors. Now you're going to look at example 1 where they intersect at a point. They're not parallel. They're not going in the same direction. So the direction vectors will not be scalar multiples. In example 2, they're coincident. They're going in the exact same direction. So their direction vectors have to be scalar multiples. In example 3, we have 2 parallel lines. So they have to be going in the same direction. So they'll be scalar multiples. And option 4, because they're skew lines, they're not parallel, they're not coincident, they're not going in the same direction, so they won't be scalar multiples. So essentially, the first thing you really need to know is that if you want to start narrowing down your options, every single time you are going to examine the direction vectors and figure out if they're scalar multiples. And then you are eliminating your options from 4 down to 2. So let's take this and let's use this information to help us out here. So example 2 says determine if these lines intersect. If they do, find the coordinates of the point of intersection. So again, as I mentioned, the first step, always take a look at your direction vectors. In this case, they're the same direction vector, which means they have to be scalar multiples. So they're going to be either parallel or coincident. So once we have that, we know that either they are going to have every single point on the line that's intersecting, or none of them are going to intersect. So what we're going to do is, as always, because we like working with parametrics better, it's easier to work with, we're going to start by writing out the parametric equations. And then, once we have the parametric equation, then we're going to take a point and we're going to test it on the other line, just like we did in 2 dimensions. And again, it's that all or nothing proposition. If one point works, they all work. If it doesn't work, then none of them works. So that's essentially what we've done down just down below. We start by writing the parametrics from our first line 1. Okay, we just took out the x values, the y values, the z values, and we turned them into 3 separate equations. And then all we did was we plugged in. We took a point from the other line. In this case, we did 1, negative 9, 9. Because it has a position vector, we've said that's always a point on our line, so that will work. So I've just taken that and we put that into each of those spots. And then we just gone and solved. So now take a look. For the x equation, we plugged in our x value for that point. It was 1. We rearranged, we get a value of negative 4 for s. For the y equation, we do the same thing, but with our y value, and we get negative 4 equals s. So those two line up. So if the third one lines up, then we're good. But we got negative 7 over 2. It's close, but it's not quite. So it means that that S value does not work for all three of our coordinates. So it doesn't quite line up. So again, we are basing this on the assumption that that point lies on line 1. If we get different S values, if we can't get one singular S value, it means that something is wrong in that assumption. And the wrong part of that assumption is that the point doesn't actually lie on the line. And if that point doesn't lie on the line, then they can't be coincident, so it has to be parallel and distinct. So our statement at the end, because the S values are not the same, 1, negative 9, 9 does not lie on line 1. Therefore, line 1 and line 2 are parallel and distinct. The next option is skew lines. So let's talk about those really quickly. So the first question we're asked is to determine if these lines are skew. So we're going to start dealing with this just like we would any other problem. We're going to start by looking at our direction vectors. In this case, we have 1, 2, 3, and we have 2, negative 1, negative 1. And we know we can't multiply the first one by any scalar to get the second one, so they're not scalar multiples. So that means either they have to be intersecting at a point, or they have to be skew lines. They can't be parallel and they can't be coincident. So our next step, once we get to this point, we're going to assume that there's a point of intersection and we're going to try and solve for it. And if we get something that is total nonsense, then it means that it has to be skew. So again, the first thing we're going to do is we're going to take our parametric equations, and just like with 2 dimensions, we're going to just take those and we're going to use substitution and elimination to help us solve. Think back to example 2, the first method, where we used the parametric equations and we got rid of the x's and the y's. Same basic idea, except this time you'll notice we have 3 equations for each line. So way too much to deal with right now. So there's a little trick that's going to help us here. We're going to ignore the z's for right now. We're going to see if we can find an intersection between the x and the y, and then we're going to test it in z. Okay, so what we're going to do is we're going to take, just like before, we're going to take our x equations and we're going to set them equal. So this one here is x equals x, and we get s equals 2t plus 3. Then part 2, we're going to set y equals y. And then you're going to notice we plugged in that statement that we got from part 1 in for s instead. Instead of s, we're putting in 2t minus 3. And what happens is, once you rearrange that, again, I'm assuming that all of your substitution and elimination skills are up to par. If not, come and talk to me and I'll give you a bit of clarification. But when you do that, when you rearrange, we get a t value of 2. So that means that at least for the x's and for the y's, if we plug t equals 2 into our equation, we're going to get a point that's going to satisfy both of those lines. But we're really not sure if it works for z yet. But before we do that, we know how to find s as well. So we're going to take in step 3, we're going to take that t value and we're going to plug it back in using the equation that we got from part 1. Now, when we do that, we get a value of 1. So at least for x and for y, we have a t value of 2 and an s value of 1 that should work. So if you plug those in, you're going to find an x and y value that are going to match. But because we didn't really factor in the z's, we don't have a guarantee that that's going to work for the z's. So our last step is that we're going to take that s and that t, and we're going to plug them into our z parametric equations like we did right down here. And you're going to notice that what happens is that when you plug them in, for line 1, we get a z value of 1. And for line 2, we get a z value of negative 1. Which means that we're not really sure what x and y are. You could plug them in and you could find out what those are. But we know that whatever they are, they're not going to give us the same z value. So because the z values are not equal, there's no point of intersection, which means that it has to be a skew line. Okay, one more part to this lesson, and this is determining a point of intersection. So essentially the same basic process as before, but this time we're going to have a point of intersection, and I just want to show you how that would look. So again, same basic idea to start. We check the direction vectors. In this case, again, they are not equal. They're not scalar multiples. So for that reason, we know that they are either intersecting at a point, one solution, or they're skew lines. Exactly the same as in, so that means that we're going to do things exactly the same as example 3. We're going to test and see if there's a point of intersection, and if it makes sense, then we know that that's the point. So again, we start by splitting up our equations into parametrics, like we did here. And then we're going to set x equal to x, y equal to y. And we're going to use that to help us solve. With x equals x, we rearrange it, and we get this expression for t in terms of s, which we can plug into our y equals y, which we did pretty much at this line here. And when we do that, we're just using basic elimination substitution. And when we do that, we rearrange it, and we get an s value of -3, which means that for x and for y, s equals -3. If we plug that into line 1, it's going to give us some point that satisfies x and y for both lines. And using our knowledge of elimination substitution, we can also find the t value as well. So again, now we have two parameters that we can plug into either equation, and they're going to give us our x and y values, but we have to check and see if it works for z. And this spot here, part 4, looks a little bit different, but essentially it's the same basic idea. We're going to test our s and t values and see if they give us the same results. The only thing that looks a little different is that we set z equal to z. But because we know that has to be true, we can do that. So all we did was we set z equal to z, we plugged in our parameters, and you notice how we get 3 equal to 3. So in this case, that makes absolute sense. It means that our assumption that there's a point of intersection is sound. And that means because the left side is equal to the right side, there has to be one solution. So now that we know there's one solution, all we have to do is find that point. So you can take t or s and you can plug it back into one of the equations, just like we did at the bottom here. And you get x value of 1, y value of -1, and z value of +3. So I forgot to write my last solution here, so I'll do that really quick. So therefore, point of intersection is 1, -1, 3. And again, don't forget to use round brackets because it's a point, not a vector. So that's pretty much it for intersections of lines. There will be one more quick video on how to deal with the distance between skew lines, but that will be in a separate one. Thanks, guys. Happy practicing. And again, ask me if you have any questions.